Let's see. We have discussed as a first chapter, we reviewed the MS threshold voltages, and then we have discussed about the geometric vector, small geometry MS devices, and the geometric effect on the threshold voltage. And we covered the length effect, and we just discussed about the width effect, and then we have seen that in classical threshold voltages there is no terms like length and width in determining the threshold voltage, but we have discussed about the threshold voltage incorporation of the length and width. And then we have summarized those effects, and then we can see that this is a long gate device and a short channel device, things like that, narrow width device, short gate device, and then these are the terms, the RJ, the curvature, and the source and drains, and substrate doping, etc., etc. And then we have deduced the relationship between these two threshold in terms of the threshold voltages. And finally, we suggest the device structure with the channel stop implants, P+, that is related to the width effect on the threshold voltage, and the threshold voltage implantation we called channel implantation. This is a channel stop implantation, and this is a channel implantation, and that is related to the length effect. Of course, it's directly related to the threshold voltage. Okay? Now, today we are going to talk about the substrate resistivity selection, and of course this topic just come from the fact that we want to miniaturize the device for the high-level VLSI. And this is the typical structure of the MOS transistors. And what we are going to talk about is what is going to be the substrate doping level. Should it be high or should it be low? We have a choice. And then which one is beneficial in miniaturization of the MOS transistor. That's what we are going to talk about. Okay? Well, first of all, the substrate resistivity has a effect on the device performance, just like this. If it is a high, we have this kind of merits. Okay. If it is a low, we have this merits. So substrate doping level has some advantage and disadvantage. For example, if a substrate level doping level is high, we are going to have less DIBL, drain-induced barrier lowering, and that is related to the figure 16. We have just seen that when we have a short channel device, and we have, where is the figure 16? That's 20. Goes, yeah, okay, here we go. It's figure 16. This part, the depletion layer, we're going to lower the potential. We call that the drain-induced barrier lowering. Okay, and that is pretty much related to the geometric effect. But anyway, if you have we're going to discuss about the DIBL later, and shortly in the next chapter, the electrical property chapters. But we have a less effect if we have a high doping level of the substrate, and then we have a less sensitivity of threshold voltage on the geometric things, and then drain voltages as well. And then it is beneficial for the ideal scaling if you have a high dopant concentration. On the other hand, if you have a low dopant concentration, the substrate concentration, then we're going to have low junction capacitance, which is inevitable. Junction capacitance means the source and the substrate, and drain and substrate. That is kind of diode, right? Low junction capacitance. And then if you have a low doping level of the substrate, we're going to have an independent threshold voltage. Threshold voltage is not sensitive to the doping level as far as the doping level is low. And we have a better sub-threshold slopes. We're going to talk about this, sub-threshold voltages, sub-threshold slopes later in the next chapter. And then we have a better backgate bias sensitivity. Backgate bias is going to be discussed in the next chapter as well. Okay? This is the figure which shows the substrate resistivity is the x-axis, and then y-axis is the threshold voltages. What you can see here in this plot is that when the oxide thickness, gate oxide thickness is 0.1 micron, this is the crystallographic direction of the substrate. If you have a MOS transistor is 100 surface, or you can make it on the 111 surface. And then in both cases, if the oxide thickness is 0.1 micron, you can see if you reduce the substrate doping so that you increase the substrate resistivity, the threshold voltages start out at about 7 volts. It approaches to the 0 volts when the substrate resistivity is higher than the 10 ohm centimeters. So can you see the changes in here? Now if you have gate oxide thickness is 1 micron, 10 times of this, it changes more sensitively it is changing with the substrate resistivity. Okay, so you can see that you better have high substrate resistivity, low doping level. And since it becomes 0, in this case we have to do something about the threshold voltages. We cannot run the MOS devices with the threshold voltages at 0. That is just a none. So we do have to make a threshold voltage control implantation to make the threshold voltage to some values. For example, in a PMOS case, it should be minus 0.7 volts, around minus 0.7 volts. So we make the substrate more than 10 ohm centimeters, high resistivity materials, so that the threshold voltage is not much sensitive to the substrate doping levels. And then if the substrate doping level is around more than 10 ohm centimeter, as you can see in this plot, the threshold voltage becomes 0. So we have to have some values for the threshold voltage to turn on the MOS transistors. We have to do some ion implantation to control the threshold voltage to get some values like PMOS case minus 0.7 volts and MOS case plus 0.7 volts. So we want to make it symmetrical. So that can be done by ion implantation, channel implantations. Here it is summarized: high resistive substrate, the capacitance and threshold voltage becomes independent of substrate doping level, and a good backgate bias sensitivity. And we do the channel implant to control the threshold voltage. Okay, so that's what we should do. In this substrate resistivity selection, if you want to make a small device, what you have to do is you have to have a substrate resistivity more than 10 ohm centimeter. Typically, this is going to be 20 ohm centimeter. And the threshold voltage becomes 0, so that you have to do some ion implantation to control the threshold voltage. That's what we have been discussed for this sections. Okay? And the next section is NMOS or PMOS. Most of the current DRAMs that is made with the NMOS, because NMOS as you know, electron has a higher mobility than the holes, 2-to-1 and even 3-to-1. So NMOS has a merit and speed. So most of the DRAMs recently are made out of these NMOS. But what's going to happen if you miniaturize the device? Do we have to have still the benefits as an NMOS compared to the PMOS? That's what we are going to discuss in these sections. Okay? Well, this is the mobility and the electric field. The x-axis is the electric field. Okay? This is the electric field, and this is the mobility. The electron mobility and the hole mobility. You can see almost 3-to-1, more than 3-to-1 high values in the mobility of electrons compared to the holes. And especially the 1-0-0 is a higher mobility than 1-1-1 because atomic density difference. Now, what's going to happen if you here you can notice that the NMOS has an advantage over PMOS more than 3 times in terms of the mobility. Okay. This is the interesting figure. This is a carrier velocity, the mobility times electric field, and this is the electric field. So the slope here is actually corresponding to the mobility. Okay? The velocity is electric field times mobility. So you can see at low electric fields, excuse me, at low electric field, you are going to have a straight line, and then that slope is corresponding to the mobility of electrons in germanium and the silicon, or the mobility of holes in the silicon and germanium. And that has been compared in this plot. The thing we have to notice in this plot is that, for example, if you go for the silicon, the holes is going to, the mobility is going to change from here, and then the velocity, it goes, end up with some high electric field right there, right? And for the electrons, where is the electrons? It starts out with the higher values of the velocity, but as it goes to the high electric field, the velocity of electron is going to be the same to that of holes. And this high electric field, it means that it's saturated at the same values. But the important thing is the holes it saturates a very much higher electric field than the electrons. So when you miniaturize the device, now you're going to increase the electric field because the distance between source and drain get closer, right? And then at high electric fields, we begin to see that the holes are beneficial than electrons because the holes is going to saturate later at higher voltages than the, than the electrons. And once it is saturated, then the velocity is going to be the same. So MOS is not different. The mobility of MOS at the holes is not much different from the mobility of electrons. So this is the typical example that the drain current and the drain voltage without saturation and with the saturation is the dotted line here. There is a huge difference between these two, with saturation and without saturation. It means that when it's saturated, the current is going to be diminished. But as you can see in this plot, this is about holes. And in case of holes, the saturated current is not much different from the non-saturated current. But still, the y-axis, the current is somewhat very much lower than the electrons because inherently it has 3 to 4 times, the mobility is 3 to 4 times smaller of holes compared to the electrons. So at high electric fields, V saturate of electrons are almost the same to that of holes. There is not much difference between N and PMOS. Okay, it should be noted that the electrons are saturated earlier than the holes. So electrons is going to saturate earlier at low voltages than the holes. That is the key point here. And here's an interesting comparison in the table. The constant electric field, we set a scaling principle, and in constant field means we want to maintain the electric field constant when you decrease the device. It means that when you decrease the gate length by factor lambda, then the drain voltage should be decreased the same scaling factor lambda to maintain the electric field between source and drain the same, right? And constant voltage means even though you shrink the device, you just keep the drain voltage the same voltages before the shrinkage. So that naturally, in this case, we're going to increase the electric field, right? Quasi-constant voltage means you just play in between of this to not to go to the extreme. That is a very industrial term, okay? So if you set a principle, constant field, constant voltage, and quasi-constant voltage, accordingly you have to have different scaling. You have to apply the scaling factor differently for the dimensions, gate oxide and the doping and the voltages, things like that, okay? And then with that, you can have this plot. And then the y-axis is the drain current, source and the current between source and drains, and x-axis is the scaling factor, which means if you move if you move to the left, it means that your device becomes smaller and smaller. All right? So what we try to compare here is this constant electric field case, the NMOS and PMOS. You have some band here because the one is the optimistic and the pessimistic case are simultaneously drawn in this plot. And then you can see a constant electric field case by miniaturization of your device. The benefit of N-type MOS still is maintained. Okay, it is not much. There is a difference. There is a gap, and that gap is kept by scaling. But if you go for the constant voltage scaling principle, then you begin to see that the N and P is approaching to the same values. So the NMOS is not much beneficial to the PMOS by scaling in case of constant voltage. Now, quasi-constant voltage, which is a very industrial term, you begin to see the striking difference. It means it is not really beneficial to get an NMOS in the quasi-constant voltage case that converges to the same values as you scale down your device. So what you can notice is that constant electric field case must maintain 3-to-1 advantage. And mobility is the still dominant factor in controlling the device. And constant voltage scaling, PMOS catches up, okay? Because the saturation velocity becomes more dominant as you decrease the size. So for constant voltage or quasi-constant voltage, which is the industrial practice, PMOS only 1.3 to 1.6 times worse than the NMOS when the length becomes less than 0.2 microns. Okay? And this is just the discussion in terms of the mobilities of electrons and holes. Now, we have to take another thing into account when you make a comparison between MOS and PMOS after the scaling down. That is impact ionization. Okay, when the device becomes miniaturized, you have seen in threshold voltage that the RJ has to be small, okay, to reduce the sensitivity to the geometry, which means when you scale down the device, you have to have a shallow junctions, and RJ becomes should be very much small. And in that case, it's just like a needle. We are going to have a high electric field concentration at this point, so that we are going to have impact ionization. Okay? So if the device is scaled on the basis of a constant voltage or quasi-constant voltage, then electric field has to increase, and therefore carriers have to have high energies relatively, which causes impact ionization to occur. That impact ionization, we're going to induce the substrate current and charge trapping in silicon oxide, which causes the shifting in the threshold voltage after some use, okay, with the time, which is a problem in the long-term reliability. And ionization coefficient of holes is much, much smaller than the electrons. So the PMOS would have a less this impact ionization than the MOS. It can put up with high voltages. Okay. So this is the one of the reasons why we have to choose the PMOS instead of MOS, even though the electron's mobility is much higher than the holes. This is another reason. There should be two reasons. One, the velocity saturation, and this, the impact ionization. You never heard of the hot holes, right? The hot electrons. What is a hot electron? Hot electrons is hot electrons. Hot electrons. It is related with the impact ionization we have been talked about. And when you are going to give a high energies to the electrons, and that energy which come from the electric of course they come from the electric field that you apply, right? And that it can be force and whatever the potential, and that energy is, if you divide it by the Boltzmann constant, that is the Boltzmann constant. Then you end up with some temperature. Okay? So the electrons which can have a high energies by electric field, then it can be regarded as an electron having some high temperature. That's why we call that hot electrons. It's not really hot in terms of the temperature, but in terms of the energies, it is related to the hot temperature energies. So this Boltzmann constant is that amazing factor. You know, anything if you want to convert it into the temperature, all you have to do is you derive the energies in terms of the newtons or whatever the unit is, and then divided by the Boltzmann constant, then you end up with some temperature. And if that temperature is corresponding to 1,000 degrees centigrade, whatever, that does not mean that that substance really has that high temperature. In this respect, you may heard of the hot electrons, but you never heard of hot holes. Why? Because for the holes, it is not going to be accelerated by the electrons by the electric field that much, just like the electrons. That's why we do not have hot holes. And then more academic term, you may say, for holes, the barrier height for hot carrier generation is much higher than for electrons, so that the PMOS is more reliable than MOS. That's what you can say. The silicon oxide, the valence band barrier is 3.6 electron volts versus 3.2 electron volts for conduction band barrier. So that's what. That's why we don't have any hot holes, even though we have a lot of hot electrons. And the hot electron is really a problem in terms of the reliability. And the problem in reliability is kind of thing that the industry has to be careful about, because that is a very crucial factor. Okay. And this is a substrate current as a function of the gate voltage. That is, a substrate current is the y-axis, and substrate current means that it's a current coming from the impact ionizations. Okay, that is going to be called the substrate current. Substrate current. And substrate current, you can see that NMOS is much higher than the PMOS. This is the gate voltage. Okay, so we have discussed of the substrate selection, and we have choice. We have discussed about the choice in the MOS and the PMOS in miniaturization, in scaling down the device. And the next topic is going to be the latch-up. And the latch-up in CMOS, the latch-up phenomenon comes only in the CMOS structure, and then the CMOS structure is going to be look like this. Almost all of the current memory devices they are made out of this CMOS structure, complementary MOS. Okay, complementary MOS. It consists of two MOS and PMOS at the same time on the same substrate, and that is going to be called CMOS. Of course, we can make the N substrate as shown in this figure, N substrate, and then set a P well, and then in this P well we have an NMOS just like this, and then N substrate we can have the PMOS, so that the PMOS and MMOS at the same time. This is just for the contact to the substrate. Okay, so here we have a PMOS, and here we have an NMOS. For the NMOS in the N-type substrate, we have to form a P well. We call this well, right? This is one example of the CMOS. We can just do the same thing on the P substrate. Okay, if you use a P substrate, then you form an N well. In this N well, you can have a PMOS. And here, if you have a P-type substrate, then you can set the MOS here. And the reason why we are interested in the CMOS instead of MOS or PMOS things is that we have almost zero standby current, low impedance, and large noise margins or wide operating supply range. Well, so these are the reasons why we are choosing CMOS for the integration. But it is another story to which CMOS is going to be taken. For example, do we have to use a P substrate or N substrate? If you choose an N substrate, it means that you're going to build the PMOS in most of the substrate, and then locally you set an N well, a P well like this, and then you set the MOS. So in this configuration, most of the device is made out of the PMOS, and then occasionally you are going to have an NMOS to make an inverter, to make a CMOS structures, right? And if you take the other way around, like you have a P substrate, then you're going to have an N well. In this case, most of the device is going to be consisting of the NMOS, and then occasionally you're going to have a PMOS locally, right? Now, which one is beneficial? Obviously, we want to make most of the device in MOS because the MOS is much faster. So this is not common practice used in the industries. We are using the P substrate instead of N substrate like this, okay? But in this discussion, we just have this configuration as a model, and then that is going to be the same. Any theories related to the latch-up is going to be applied for the other CMOS devices as well, exactly the same thing. So what is the latch-up? Well, if you have a NMOS and PMOS at the same substrate, like this, then we are going to see the parasitic circuit, which is the electrons may travel for this in the N substrate, and then this is a P plus that the PMOS source is actually, and then the N substrate, and then here is the P well, so N plus, P plus, and N substrate, and the P well. That is kind of bipolar transistors. So if this bipolar transistor is going to be triggered by the applied voltages, the VDD, on this N plus, then it is going to have current I sub Rs, current, and this current is going to be huge, accelerated through this bipolar transistors by the value beta of the gain of the bipolar transistors. And then that current is also going to be collected in this vertical bipolar again, which is N plus in an MOS, and then P well P, and then N substrate, the N plus P N bipolar. And then it's going to work as a biasing the base of this vertical transistors, and then there is going to be a tremendous current can occur, and then going to be collected through this RW to the contact of this MOS to the P well. So this is not what we want. This is not the current path we want, but it does happen because the CMOS, the MOS and PMOS are supposed to be built on the same substrate. So this current path is possible. It is not always possible, but it is possible. And then if you look into this circuit carefully, then you can immediately see that the two bipolar are connected to each other. And then it can be triggered to have a large current. So, what is the problem with this latch up? The real problem is not the current itself, but the heat which is going to be generated by the Joule heating through this current. The current level is very high, and then if the current level is high, then each tiny CMOS, which has been 10 or 100,000 of them are located in the same place. Each generates the Joule heating through this latch-up current, then it's melted down. So the burning is the problem. The current itself is not a problem. We have to prevent the latch-up because the device is going to be ruined, not just the one-time thing, but it's going to burn out everything. So the latch-up has to be prevented somehow. Okay, and that is the main reason why we have to deal with this latch-up carefully. Okay, and the theories that we are going to develop is based on the student, Stanford University in 1980. He wrote a PhD thesis on the basis of the latch-up phenomenon for the first time. Okay, and then this lecture is based on his thesis. Okay, we're going to talk about this latch-up thing on Wednesday. Have any questions? Okay, I'll see you on Wednesday then.